At enterprise scale, a recommendation engine is a battle against physics. Hundreds of millions of discrete data points must be funneled down into a single, personalized output in the blink of an eye. When you design the systems behind surfaces like Amazon's homepage carousels or Instacart's cross-sells, the prompt is straightforward. Serve each shopper a distinct set of products they are highly likely to buy. The constraints, however, are brutal. The active catalog contains roughly 300 million distinct items. At any given moment, the system is hit with hundreds of thousands of queries per second. From the exact millisecond the user loads the page, the entire system has a strict latency budget of less than 150 milliseconds to return that personalized list. Running a complex deep learning model against 300 million products simultaneously requires massive compute. Doing it in 150 milliseconds is impossible. The servers would simply time out. At this scale, the primary engineering problem is architectural. You have to build a system capable of filtering an ocean of data down to a highly relevant puddle before the heavy machine learning even begins. We also have to define what the algorithm is actually trying to achieve. Video platforms optimize for watch time and attention. E-commerce engines must optimize for revenue. If you train your model to optimize solely for click-through rate, the system learns to surface cheap, irrelevant clickbait. Users will click, but they won't buy. Conversely, if you optimize strictly for the highest conversion rate, the model takes the safe route. It fills the screen with toilet paper, batteries, and things the user already buys on repeat, effectively starving user discovery. This formula shows the target, expected value. Multiplying the probability of purchase by the price tag calculates a product's true worth. To calculate this across 300 million items in 150 milliseconds requires a three-stage funnel: retrieval, ranking, and re-ranking. Solving the latency bottleneck while aligning the math with actual gross merchandise value separates a basic machine learning pipeline from a staff-level production architecture. Stage 1 is retrieval. The objective here is high recall and ultra-low latency. In roughly 15 milliseconds, the system must aggressively drop the active pool from 300 million candidates down to about 1,000. To achieve this speed, the engine utilizes a two-tower architecture. This diagram outlines the setup. One neural network tower processes user features. A parallel tower processes item features. Both project their data as mathematical vectors into a shared geometric space. Using an approximate nearest neighbor search, the system locates the user's vector and instantly grabs the 1,000 closest product vectors. But the nearest neighbor index operates on pre-computed embeddings, meaning it can miss sudden shifts in real-time user intent. To cover these gaps, the system queries a high-speed key-value store in parallel, fetching pre-calculated co-purchased graphs and recently viewed items to blend into the candidate list. The retrieval later operates as a blunt instrument. It trades exact precision for the sheer computational speed needed to build a manageable candidate pool. With the pool reduced to 1,000 items, the funnel narrows into stage 2, ranking. The system now has a 40-millisecond window to score these candidates with precision. Because the candidate list is much smaller, we can deploy a heavier, multitask deep neural network, specifically a multi-gate mixture of experts, or MMOE. This diagram shows the MMOE in action. A single retrieved product node passes into the network, outputting 3 separate predictions: the probability the user clicks, adds to their cart, and actually buys it. Generating these probabilities simultaneously differentiates browsing curiosity from serious purchasing intent. The system isolates the purchase probability and multiplies it by price, ranking candidates strictly by expected value. This multitask calculation solves the optimization paradox. The model weighs the likelihood against the financial margin, satisfying both shopper and platform. Beautiful architecture fails if the underlying data is flawed. When you apply standard ranking algorithms to real human shopping behavior, the pipeline fractures in 2 distinct ways. The first pipeline issue is delayed feedback. Shoppers often click an item, leave the site, and complete the purchase 3 days later. This delay creates a label maturation gap. The fresh training data feeding the model is temporarily missing the positive purchase signals. The model learns to systematically underscore high-consideration items, like furniture or electronics, because those purchases rarely happen on the first click. The second major issue is the returns loophole. This timeline graph tracks a common data failure. A user purchases a product, registering a strong positive signal. 2 days later, they return it. The system must retroactively overwrite that green purchase label with a red negative correction. Without this explicit negative correction, the system optimizes for regret. The model learns to aggressively push low-quality, highly clickable products that look great in a thumbnail, but are immediately returned by real buyers. We now arrive at stage 3, re-ranking. The model has selected its top 30 ranked items, but only 10 will fit in the final display carousel. Machine learning models operate on historical patterns. They are completely blind to real-time supply chain collapses or warehouse shortages. Recommending a highly relevant product that is completely out of stock instantly damages user trust. To prevent this, the engine applies hard business filters at the very end of the line. This diagram shows the final purge. The top 30 list runs through live inventory databases and user profiles. Any item flagged as out of stock or already owned is immediately struck from the list. Next, the system takes a brand new, unranked product, one with 0 historical data, and forcefully injects it into the final top 10. This is an exploration budget. The system uses contextual bandits to intentionally display untested products. This solves the cold start problem and ensures the platform doesn't become a monopoly for dominant sellers. Raw machine learning predictions are ultimately just suggestions. Hard business constraints and inventory realities override the math to dictate what the user actually sees. Pulling back, we can map exactly what happens the moment a user initiates a page load. This architecture map traces the complete data lifecycle. The request hits the API gateway, which immediately pulls context from the online feature store. A high-speed data pulse splits, triggering the 2-tower nearest neighbor search, the co-purchase graph, and the cached history simultaneously. The 1,000 gathered candidates bottleneck into the ranker for multitask scoring, hit the final re-ranker for inventory filtering, and arrive at the UI as a fully rendered slate. Parallelizing these stages across distributed systems is the only way to execute this volume of computation and guarantee a personalized, in-stock recommendation within 150 milliseconds. Designing this funnel requires accepting deliberate trade-offs. You balance the depth of heavy, precise multitask models against the uncompromising physical limits of server latency. You also balance short-term revenue against long-term marketplace health, deliberately sacrificing guaranteed clicks to enforce exploration and seller diversity. Success at this enterprise scale ultimately demands a perfect, seamless alignment between high-dimensional math and uncompromising physical server limits. Ultimately, enterprise-grade AI is the discipline of compressing complex calculus into an impossibly narrow 150 millisecond funnel.